So this is like yesterday's thing, where if we use the above formula, this is an inverse square type thing, which means the force is related to the distance with an inverse relationship because the force gets bigger if the distance gets smaller. You put them closer together, they'll have a greater force. So that's what makes it inverse. And it's inverse square because it's squared down there. If it were just F equals this over D, then you put them twice as close, the force gets twice as much. But because this is squared, you put them twice as close, and the force is now 4 times as much. And I didn't say this yesterday, but if you put them 3 times as close, because of that squared right there, it's not 6 times as much, it's 9 times as much. So you put them 3 times as close, the force is 9 times greater. You put them 4 times as close, the force is 16 times greater. So in this case, you don't need you need the formula to see that there's an inverse square relationship between the force and the distance, but you don't need to actually do the formula. It tells you the force here, so it tells you the charges, which you don't need those. It tells you the force was 10 newtons when they were 2 meters apart. And then it says, okay, what would be the force if they're 1 meter apart now? So you put them twice as close, the force will be 4 times as much, and you already know that just because there's an inverse square relationship. So instead of 10 newtons, the force would now be 40 newtons. There, I can talk. And we'll do a couple more things like this. There's a CTPA question that is like this, where you need to know what this inverse square relationship means. Today, we'll be using the rules for series and parallel circuits to figure out total resistance, and we'll be drawing circuits like you did yesterday. We'll also be learning a new symbol. This little symbol here, this squiggle, it's more of a zigzag because it has pointies. That is the symbol for a resistor. And it tells you resistors down here. I will note on the answers I posted for this, sometimes when it says that there are lamps, sometimes I put little squiggles for resistors for today's thing and tomorrow's thing. I think, I don't know yet. Y'all should use the symbol for lamp, which is that circle with the X in it, that little railroad looking symbol. I put resistors, and technically they are resistors because anything, the reason that lamp lights up is its little filament has a lot of resistance in it, and it has so much resistance it heats that little filament up red hot. Anyway, for each of these problems it's asked you to draw a circuit, so I'm going to go ahead and draw a circuit for this one, number 7. It says 200 ohm resistors are connected in series. Oh, and they're connected to a 1.5 volt battery. When you draw these, it's important to, I'm supposed to be undid here. So this is a battery, and I think I said, I don't know, I might have forgotten here. This battery symbol is like this because the first battery that Alessandro Volta made had little things like that. It had I'll draw this over here. It had a big disc and a little disc, and a big disc and a little disc, and so on. And that's how they made. Each of these discs had different electric potential. Remember, the voltage is the same as potential difference because the difference in electric potential between each volt made the electricity want to flow from one plate to the other plate, or disc, whatever. Anyway, that's why the symbol for battery is like that, because that's what the first battery looked like. He made that first battery, Alessandro Volta. And then he's like, dang, I can do this. And then they fixed it so it worked better. But this is what the first one looked like. Anyway, I'm going to label my stuff. This is my 1.5 volt battery. And I got to say how many ohms my resistor is in my diagram. So let's see. This one's 100 ohms, and this one is 100 ohms. This is supposed to be a little omega right there. Mine kind of look like R's. There, that's a little better. All right, this question does ask for the total current, but we're going to do that tomorrow. Today, I'll do the total resistance. So, in order to find the total resistance, how do you spell resistance? We need to look at our table up here. I got my series circuits, which are like this, and my parallel circuits, which are like this. And this one is a series circuit. So we're going to use the series rules. So to find the total resistance, for series, total resistance is R1 plus R2 plus R3. That just means that you add it up. So, and it just says R3 just in case you have more than, just in case you have 3. And if you have 4 or 5, then it's R1 plus R2 plus R3 plus R5. I skipped 4. You just add them up, however many you have. So our total resistance, since we got 200 ohm resistors, is 100 ohms plus 100 ohms equals 200 ohms. There we go. So that's easy. I'm going to do a parallel example, and I'm going to do it using this other one down here, but I'm going to have to scroll. So remember this for a minute. We're going to find the total resistance for a parallel circuit. So since it's a parallel circuit, we've got to use these other rules here. This total resistance formula looks all weird, but if you use a calculator and you use these parentheses, it'll be fine. It's 1 over R1 plus 1 over R2 plus 1 over R3. Because it's a parallel circuit, it can kind of split up the resistance between its little paths. So that's why it's different. It's not just, you have to go through all these, so it's this one and this one make 200 ohms. Let me show you an example here. I'm gonna erase this so I can go down there. Here we go. I think. I could just put it over here. All right, I'm going to do this little section that's parallel. Now this thing is a series circuit with a parallel section. These two batteries are in series with each other. We're not dealing with something as complicated as this yet. I'm just going to show you the total resistance for this part of the circuit. So, let's see. Our total resistance formula is 1 over R1 plus 1 over R2, etc. plus 1 over R3. We've got 5 of them this time. So when we do this, I better give myself a little more room there. When we do this, we're going to say 1 over, each of these is 1.1 ohms. 1.1, 1 over 1.1, 1 over 1.1, 1 over 1.1, and 1 over 1.1. In order to do a better example here, I'm gonna show this one with a little bit different things here. Let's say that instead of 1.1, because this is just going to be like a math problem, I want to show y'all a couple of different ways to do it. So one way is you can just put it in the calculator with those parentheses I showed up there. So the whole bottom has to be in parentheses, and each thing has to be in parentheses. But instead of 1.1 for each of these, I'm going to say that, okay, this one is 10, this one is 5, this one's 20, and the rest of them are 20 here. So the way for us to do that, we could just put it in the calculator, or we could say that the total resistance is, we could put them all in decimals and then put it in the calculator. So, 0.1 plus 0.2 plus 0.05 plus 0.05. You could do that. and then put it in the calculator, that'd be fine. Or you could make your fractions in different ways. So when you look at my answers today, you'll see that I showed different ways. I chose different ways on a couple of different problems to do. So you could make all these fractions the same. So the least common multiple out of 10 and 5 and 20 would be 20. So I could turn all those fractions into 20ths. So 1/10 would equal 2 20ths, and 1/5 would equal 4 20ths. And then you got 1/20th and 1/20th and 1/20th. So this is a convenient way to do it in your head if you want to do that, which I like doing that, it's fun. So when you add all those up, you got, let's see, 4, 5, 6, 7, 8, 9 20ths. 9 20ths. And then dividing by a fraction is the same as multiplying by its reciprocal. So instead of 1 divided by 9 over 20, this is the same as saying 1 times 20 divided by 9. And that's not a clean number, but it's going to be 2.22222, right? That's the secret about ninths, is ninths are always repeating. 1/9 is 0.11111, 2/9 is 0.22222. So 2 times 9 is 18. There's 2 left over. That's 2 out of 9, which is 2.2222. Anyway, our total resistance would end up being 2.22222 ohms. But you're welcome just to use a calculator, or to do it, to change them into decimals, or to do the fraction way, to find the least common multiple and add them up so that you can add up the fractions properly, and then do the reciprocal thing. But there's many different ways, and they all work, and they're all just fine, including just the calculator way. Make sure you use your parentheses appropriately, though, otherwise it'll mess up. Sound good? See if y'all can try that out. Remember, you've got to draw a picture for each one. It asks you to, so you don't need to remember. Make sure you use the proper symbols. The little X for volt, the little squiggle for resistor, and the little plates for voltage.